The next major topic I'll cover is system and network analysis. In this analysis approach, physical devices are viewed as systems which interact via their inputs and outputs. System analysis can be used to break a complicated design task down into a number of simpler subtasks. In this video, I'll introduce the concept of a system and show simple applications of this kind of analysis approach. It can be really convenient to represent a physical device as a system. A system is represented as a box with one or more inputs and one or more outputs. The definition of the inputs and outputs is somewhat arbitrary and depends on the application, but inputs are usually considered to be something that the external environment provides to the system, and outputs are something that the system provides back to the external environment. The inputs and outputs are called signals and are most often functions of time. In systems analysis, we're usually no longer really concerned with the actual device or devices that the system represents. We're more concerned with the mathematical relationship between the inputs and the outputs. This mathematical relationship is called the input-output equation, and it's usually represented as y is equal to some function of u. In this model, the system is viewed as more of an abstract entity that performs this mathematical relationship than a physical device. System analysis is really pretty much the same as what we've already been doing. The main difference is in the frame of mind. For example, for this circuit, suppose we want to determine the current I. We can calculate a value of current for this particular voltage. By Ohm's law, the current is equal to the voltage divided by the total resistance. The actual analysis approach, or the mathematics we'll use when we look at this circuit from a system standpoint, doesn't change all that much. The difference will be that we'll need to define specific things as inputs and outputs. Another thing to keep in mind is that in system analysis, we're concerned with the functional relationships between inputs and outputs rather than the numerical values themselves. When setting this circuit up as a systems analysis, we need to define inputs and outputs. The input for this circuit could be considered to be this voltage source. The voltage is provided to the circuit. The output is usually defined as the parameter we're looking for. It's provided to us by the circuit. Since we're trying to determine the current I, that's what I'll use as my output. One potentially confusing thing about systems analysis is that the definition of input and output are somewhat arbitrary. It would be easy, for example, to consider the voltage across this resistor to be the output. Now, for this system, the output current is the input voltage divided by 30 ohms. The equation is basically the same as that used in the previous slide, except that the input, Vn, is considered to be a variable now, and the output is a function of that variable. From a system standpoint, we're now modeling the circuit this way. We're no longer concerned with this physical circuit itself. Our model is just concerned with the mathematics associated with transforming this voltage to this output current. Since the input's the applied voltage, and the output's the current, this is the input-output equation for the system. Once we have this input-output equation, we can find the current for any value of voltage. For example, if the input voltage is 10 volts, the current will be 1/3 of an amp. The system representation makes it easy to evaluate how changes in the input affect the output. Next, I'll talk about block diagrams. Block diagrams in general provide a graphical representation of the interactions among systems, or among different components of one system. One application of this is in mathematical operations. Block diagrams allow us to represent what may be a complicated mathematical relationship in terms of simple components. An example of this is Newton's second law, which says that the sum of the forces applied to a body equals the body's mass times its acceleration. Since acceleration is the derivative of velocity with respect to time, this can be written as m times dv dt. If we rewrite the equation, velocity is 1/m times the integral of the applied force. We can represent this equation as a block diagram as shown here. If the input's the force, there are two mathematical processes going on, a multiplication by 1/mass and an integration. This representation makes it easier to assess the effects of the individual component in the original equation. So far, we've just talked about using block diagrams to model and analyze existing devices. Another application of block diagrams is to help with system design. In the design process, a block diagram can help us separate different components or subsystems of the design. Then the subsystems can be designed separately and combined later. If we identify operations that we need to do, we can create devices that implement the desired operations. Creating a physical device, such as an electrical circuit, to implement a desired mathematical operation is called realization. We'll talk more about realizing mathematical operations with physical circuits later in the course. A home heating system contains examples of all of the blocks we've discussed so far. This is a block diagram of a typical heating system. It includes a thermostat, which is our interface with the heating system. The thermostat accepts two inputs, the desired temperature in the house and the measured temperature. The output is a decision as to whether to turn the furnace on or off. This decision will generally be based on a difference between the desired and actual temperatures, so there's likely a subtraction process that's going on here. The thermostat output is an input to our next component, the furnace. The furnace output is heat, which is also input to the house itself. The house, since it's not perfectly insulated, will lose heat to the outside atmosphere. The house output that's actually of interest to us, though, is the temperature of the house itself. The house temperature, resulting from heat addition and loss, is the result of an integration. So representation of this block will include an integral. In order to use the house temperature to control the furnace, we have to measure it with a temperature measurement system. This system will have as its input the actual temperature, and it'll output a voltage signal that can be provided to the thermostat. Multiplication by a constant to convert from temperature to voltage will be implemented in this block. Predicting in advance the behavior of this entire system can be difficult. However, the individual components of the system are readily modeled and designed. For example, the thermostat could rely on simple logic. If the actual temperature is too low, turn the furnace on. If the temperature is too high, turn it off. Choosing a furnace also becomes a relatively simple task. We just need one that's large enough to add heat to the house faster than the house loses it. In this way, we can design the overall system component by component rather than customizing the design for every single house that needs a heating system. Those are the basics of system analysis and design. The general idea is that design and analysis can be simplified by breaking a system down into simpler components and then designing the components individually.